So 9.2, we're going to go back to the idea of power series in general, and we're going to look at properties of power series. And again, what usually happens when we're looking at new mathematics, whether it's exponents all the way up to calculus with derivatives and integrals, is that at some point when you've been introduced to this new thing, we look at properties. And the idea about properties of something is how can I manipulate it? Can I pull out constants? Can I distribute over addition? How can I rewrite it in ways that makes it easier to work with and to deal with? So the section begins by having us look at an example of our old pal, the geometric series, and think about that as kind of like an example of a power series. So let's remind ourselves of this for a second. So a geometric series is something where you multiply by r every time to get the terms in the series. And if we had something like the integral, let's say as k goes from 0 to infinity, of some number like 1/2 to the k, then this would be an example of a geometric series. We would have 1 plus 1/2 plus 1/4, etc., where each term is arrived at by multiplying by 1/2. And because this is an example of a geometric series, if the multiplier is a value, the r value that you're multiplying by is less than 1 in size, then you know that it converges, and there's a formula for that convergence. So in this case, r value is 1/2, which is less than 1. So the result would be the value of the first term, 1, divided by 1 minus the r value, which is 1/2. So in this case, we could do that arithmetic, and we could get a 2. But in general, this is true for any r. So as we've seen, this formula holds. This is true for any r with an absolute value less than 1. That any number in there r with an absolute value of less than 1, then you can use this formula that you have 1 over 1 minus r for this specific case. Now, of course, we could also start with a different number than 1, like a 7, then every term here would have a 7 on it. But you can also imagine that that just got factored out of the summation, and then you would have this simple form of the formula. So let's look at this in the light of the idea of a power series. So what did we introduce with the idea of a power series? That it's like a fixed series, except that you introduce an x variable. So consider that I wrote the exact same thing I had up there, but instead of putting a specific value in there, I put the variable x. So then this is 1 plus, and then you multiply x each time, and you get x plus x squared plus x cubed, etc. And so this is an example of a power series. It's an infinite degree polynomial. In this case, the coefficients in front of each term are all a 1, so it's a very simple example. It's kind of the simplest example of a power series that we can start with, because all the constants, coefficients are just 1. Well, because you have x being some number, which you're multiplying by each time to go to the next degree term of the power series, that creates a geometric series. So the simplest form of a power series, which is where all the coefficient constant terms are the same number, is an example of a power series, is an example of a geometric series. And that means that if you plug in a value for x, that is less than 1 in size, then you get a convergent geometric series, and it would converge to the formula above. So that means that this is going to be equal to 1 over 1 minus x when the absolute value of x is less than 1. Questions, comments, discussions about this idea? So again, we can think of this like an infinite polynomial. Then this over here is the domain. Meaning these are the values you can plug into the polynomial, the function, and get an answer. So it will seem a little funny, sort of a little backward, but you can also then consider this the other way around. So that means that when the absolute value of x is less than 1, 1 over 1 minus x is equal to the result you get if you plug x into this infinite polynomial. And so this is our first big idea to think about as we start to look at these power series. That power series, these infinite degree polynomials, give us an alternate way to calculate the value of a function. I alluded to this a little bit last time with e to the x, but normally in this case it doesn't make a lot of sense because the function on the left, right, this function over here is pretty simple. And it's much simpler to plug in a number for x there and see what I get than it is to try to plug in an x value here and then recognize it to be a geometric series, and then it goes right back to the formula that I would have just had to evaluate it. But the idea is we always like having two different ways to think about things, having two different ways to look at things or to view things. And that's what power series allow us to do. And we'll just have to understand and see the value of that as we get used to them and start to use them to do more things. So the basic idea is that a power series is an infinite degree polynomial. And like any polynomial, there's the possibility that there's values that work and values that don't. Well, actually, for all other finite polynomials, the domain is always infinite, but all real numbers. But with an infinite polynomial, then all of a sudden we possibly have values of x that cause the series that creates to diverge. And therefore, it's possible that an infinite polynomial degree will have a restricted domain, and this is the perfect example of that. But that in that restricted domain, the results you get from that infinite degree polynomial function, from that power series, are the values that could be thought of as expressed as some function. Like in this case, 1 over 1 minus x. All right, so we'll have to see this done in some examples and things like that. But before we do that, we give the general definition of a power series, which we've already introduced at the beginning of the last section, but they do it formally, so let's just follow along with that. This is on page, let's change color. On page 676 is the definition. A power series has the general form and it's a infinite summation as k goes from 0 to infinity. And as we saw before, each term of the polynomial might have some coefficient value in front of it, just like a regular polynomial. And then instead of just writing x to the k, we write x minus a to the k, with the idea that a is where this particular power series is centered. And so the simplest way to think of why that's important, or why we frame things that way, is that one of our beginning examples of these kind of polynomials is the Taylor polynomial, in which you're thinking of creating a point of tangency to a function and then generating a polynomial that approximates that function at that point of tangency. So in those cases, the a value would be the x value of the point of tangency for the Taylor polynomial. And in general, we're going to understand a little better what it means to center a power series somewhere. And the thing to notice about why we say that it's centered at A is that whenever you have something of this general form, this isn't in the definition, so I'm going to write it in a different color, but let's say you have your power series as some polynomial like this, that notice that when I plug in a when I plug in an A value, that causes this little binomial expression, as long as the k power is bigger than 0, to always come out to be 0. And so that will always be the constant c sub 0. So whatever the first constant term is in the polynomial, when you plug in a into this general form, everything drops out except that first constant. And so it's the sort of the way we think about this is that at a, you have this constant that's very clear, and then as soon as you leave the value of a, then you have some sort of power series polynomial that needs to be evaluated. But you can always just plug in a and get that first constant in the general form. Okay, so let me take away the blue stuff here, because that's not part of the definition, but just sort of keep that in mind. So yeah, so this is the general way that we write. And so let me introduce some of the language that it explains in the definition without copying it all down. It says where a and c sub k are real numbers, those are just constant values, and x is the variable. So x is the thing where you can plug in different values. That's why it's a function of x. The c sub k's are the coefficients of the power series, and a is the center. The set of values of x for which the series converges is its interval of convergence. The radius of convergence of a power series is the distance from the center of the series to the boundary of the interval of convergence. So that's kind of hard to understand, and to follow, we kind of have to see that with examples. So let me just write up these words, and then we'll look at their definitions and meanings. So we have something called, we're going to let this be a R value, a radius of convergence. Again, converge or diverge was our big phraseology for chapter 8. Does a series converge or does it diverge? And so now that we have sort of a power series function, then there will be some values of x for which when you plug them in, you get a series that converges and the polynomial has an answer. And there will be some values of x potentially which cause it to diverge. And so that creates values that work and values that don't. And that creates a domain. So in this definition, they introduced the concept of a radius of convergence, and there's, I'm going to say, see this figure on the page 676, it's figure 9.14, in which they talk about the fact that if you think about what is the domain, you know that A is in the domain of a power series, because as I just discussed, if you plug in an A, you just get a constant C sub 0. But the question is, as you plug in x values different than a, does it still converge or not? And so that means that imagine you have an a value on a number line, that as the x values leave from a, get a little bigger than a or a little less than a, then all of a sudden there's a question as to whether the power series will give you an answer or not, whether it will converge or whether it will diverge. So the radius of convergence is kind of like how far you can go away from a. Radius of convergence will be sort of how far away you can go from a and still get the series to converge. And we'll see some examples of that next. So that's the idea. And let's see, give myself some more space. I cannot. So let's look up here, just because we just did an example. So in the example that we did up here, where the domain of P of X was all values of X less than 1, you can see that I can imagine this original power series was C sub k times X minus A to the K, where C sub k was equal to 1 for every value, and A was equal to 0, so it just dropped out. So when that happens, we got this particular power series. So in this power series, the A value is 0. So if I try to discuss the idea of the radius of convergence here with our previous example, and I imagine it on a number line, centering it at my A value is 0. And we looked at our work up here to see that this only gave us convergence when the absolute value of X was less than 1. So that means that you can go up to a 1 or down to a negative 1, and that in this range, you get convergence. So in the example we looked at before, in terms of the language of our new definition, the radius of convergence was 1, because you can deviate away from the A value of 0 a distance of 1 to the right or to the left, but not equal to 1, not more than 1. So you had an R radius of 1, and that gave you a domain where X has to be less than 1. So that's an example of how we could use this language of radius of convergence. Again, that's basically how far you can leave away from the A value in the power series before you, end up diverging. Okay, so questions about that before we look at some examples to try to illustrate this with specific other problems. Point of correction, DVC math lab hours for this week have indeed changed to 10 a.m. Oh, so it looks like I just noticed that Maz put up a correction point. That's great. So that actually the extended hours are already this week. So it's just 10 to 2 and 3 to 7. And there'll be student tutors for calculus during these hours. Great. Good. So you don't even have to make the adjustment for next week. So for example, if you have questions about this discussion today, you could go from 3 to 7 anytime today after class and get help from the tutors to work with this power series material. Okay, so no questions. I'm going to go ahead and erase this. Let me do this in the right order, which I often forget to do. And then we'll look at some examples because I'm out of space on this page. Seems very short. Strange. Okay, so not what I want to do, not in red. So looking at page 676 still, we're going to look at example 1. So for example 1, it says interval and radius of convergence. Find the interval and radius of convergence for each power series. So looking at A, it's our first example. We're supposed to find the interval and radius of convergence for, and it has the summation as k goes from 0 to infinity of x to the k divided by k factorial. Okay, so this is going to be a good example of how our work will begin in chapter 9 about the kind of stuff we have to do. This is basically the type of problem we're going to be working with for the next several sections, or for the rest of the chapter, in which we are given a power series and we need to find out where it converges. So it used to be in chapter 8, it was simply, does a series that doesn't have a variable converge or diverge? Now that it has a variable, it's more of where does it converge and where does it diverge for the values of x that we might plug in, which ends up being what is the domain of this series. Okay, so if we are trying to figure out whether something converges or diverges, the typical idea before was that we had a bunch of tests that we could use. We had the divergence tests, we had the integral test, the ratio test, right? The root test, a bunch of tests that we could use. So now we're going to start to apply those again. And the difference will be is that there'll be a variable involved and we'll kind of have to solve it like an equation. So let's use this as our first example. First, let's look at this just to warm up to what this notation means, because I'm sure it's all still very confusing for many folks. And as always, one of the ways to try to do that is to write out some of the terms. So what does this series look like? When k is a 0, x to the 0 is in the numerator, is a 1, and 0 factorial is defined as 1, so our first term is 1. When k is a 1, then you have x to the 1 power divided by 1 factorial, which is 1, so you have x. When k is a 2, you have x squared divided by 2 factorial. Then you have x to the 3rd divided by 3 factorial, etc. So this is an infinite degree polynomial. This is a power series. You can think of this as a function in x. And every time you plug in a different value of x, you will get a different series that will potentially converge to a different number or possibly diverge, and then that x value is not in the domain. So we can see, for example, that there's no, the format normally in general is x minus a to the k. So if you just have x to the k, that means that a is equal to 0. So we have x minus a to the k, but a is equal to 0. So that means if we're trying to think about a radius of convergence, that we're imagining that the domain of this function starts at a 0. I can definitely plug in a 0, because if I plug in a 0 into this polynomial, I just get 1. So this converges at 0, but as soon as I plug in something that's not 0, I then have to ask, would the series I get converge or not? And that means that we start going above or below 0 with our values of x. Then we have to see whether it converges or diverges. And how far we can go to the right or to the left is called the radius of convergence. And the interval we get is called the interval of convergence, and that's what they're asking for in this problem. So in this problem, they're saying find the interval and the radius of convergence. So we're supposed to come up with an R value, which is how big or how far we can go to the left or to the right from 0. And that will produce a left value and a right value, which is our interval of convergence. So that's the goal of the problem. So I've basically tried with this discussion to clarify what the problem is talking about and what the goal of the problem is before we actually try to do it. Any questions about the statement of the problem? Any confusion we can discuss or I can try to clarify or help with before we talk about what to do?
Professor, so the x minus a part, so that basically comes from when it was first introduced as a Taylor polynomial?
Or even just a power series. So the page that I just erased and above, still on page 676, is the definition of a power series. And in the general form, they wrote it with this x minus a format, right?
Right.
And the idea is that it's centered at A. And we talked about why that is. You know, you're not used to that yet, so it's hard to understand why. But the big idea is that that's the way it is. And so if we have, as we do in this first example, just x raised to the power of k, that looks more like a normal polynomial the way we would write it with an x term, an x squared term, an x cubed term. But we have to recognize that in its simple form like that, that's because a is 0. And more importantly, that if you plug in a 0, then all the x terms go away and you just get a constant. So of course the series converges, and of course 0 is in the domain of this infinite degree polynomial power series. Does that make sense?
Yeah, I see that. Okay.
And I'm pointing that out because happily we'll have many more examples like this where a is equal to 0. But there will be examples where all of a sudden a is not equal to 0, and then that really throws students off when they first get there if they didn't recognize that when you don't have an a written in there, it's just because it's 0, and that made everything look simpler. Other questions about the statement of the problem and what the goal of the problem is? All right, so I'm going to, again, make a little bit of effort to try to connect this back to some of the work that we did in Chapter 8 and why those tools are used. So imagine, again, that this is a p of x, that this is like a function in x. And so imagine you had like p of 2. So I'm kind of going over onto the number line and imagining that I'm plugging in a 2 and trying to see if that's in the domain of the function, if I would get a series that converges. So p of 2 would be the summation as k goes from 0 to infinity. Now let me just point out, I'm writing this in blue because this is not how to do this problem. This is just to understand why we do what we're going to do when I do the problem for you. So if I had plugged in a 2 into this thing, then I would get 2 to the k over k factorial, and I would be asking in Chapter 8, does that converge or diverge? We would have a specific series with no variable in it, and then we would be looking at that series and trying to do some sort of a test to tell it whether it converged or diverged. Like we could say, well, do the terms go to 0? If they don't, then it diverges by the divergence test. If they do, then I don't have any information and I have to use some other test. Do I think I could do an integral test or a ratio test or a root test or compare this to something else and use a comparison test? So this would be, as soon as I plugged in a number for x, this would be a Chapter 8 problem. If I plugged in a 2 and I was looking at trying to see if the series I get here converges or diverges, what test does anybody think we might use? So let's do this as a warm-up problem. Let's have you guys take this series. Oops. Here's the series. and try to figure out if it converges or diverges. This is Chapter 8 review, because this is the stuff from Chapter 8 that we have to have in mind in order to move forward with Chapter 9 problems. All right, well, let's just do that. So I'm going to take a couple of minutes. Let's say 5 minutes. So I'm going to come back in about 5 minutes. I'm going to go ahead and give you guys 5 minutes to just see if you could determine if this series converges or diverges, and try to think about how to do that. And if you're not sure how to do that, you could even flip back to some pages in Chapter 8 if you have a physical book or if you have the book online. But it's very important for us to move forward in Chapter 9 that you're thinking like this about Chapter 8 problems and about the work that we did there. So yeah, I'll shut up for 5 minutes. Okay, has anyone been able to develop an opinion about whether this series converges or diverges? I see converges. Lucas? And what test would you use to support that? Ratio test? Perfect. So for those who have some memories of Chapter 8 work or have some comfort with it, one of the things about this particular series that would probably tell us to use the ratio test is that there's a k factorial. When you have a factorial in there, you can't really use the integral test because you're not going to have a continuous function with a factorial in it that you can integrate. You don't want to use the root test because it doesn't even make sense with factorials. So yeah, the ratio test is probably our go-to test. We use that most frequently. You'll be using that for most of our problems in Chapter 9. We'll use the ratio test. So specifically, if you really just didn't know what to do with this, I would strongly recommend that you go back and do and review some Chapter 8 problems and focus specifically on ones with the ratio test, because that's going to be used a lot in Chapter 9. And if you don't feel comfortable with it or see the idea of using it, it's going to really throw you. So let's apply to this case. What would it look like? And so for the ratio test, we take the limit as k goes to infinity of the k plus 1 term divided by the kth term, which is what's in the series itself. So the k plus 1 term is 2 to the k plus 1 divided by k plus 1 factorial. Then I would divide that by the k term, which is what's in the series, and since that's a fraction, I multiply by the reciprocal. So that would be k factorial over 2 to the k. And the idea with the ratio test was when you take the limit of the k plus 1 term divided by the kth term, if that limit is a value less than 1, then it converges. If it's bigger than 1, then it diverges. If it's equal to 1, then the test fails to provide any information. Yes, Chapter 8, fresh, fun. Well, in this case, we can do some simplifications. So let's say I rewrite this just to make it easier and more obvious. So this is equal to the limit as k goes to infinity of 2 to the k plus 1 over 2 to the k times k factorial divided by k plus 1 factorial. And when you take 2 to the k plus 1 and divide it by 2 to the k, you subtract the powers. So this whole thing here becomes a 2. And when you take k plus 1 factorial and k factorial in a fraction, k plus 1 factorial can be written as k plus 1 times k factorial. You can pull out the first multiplication problem, and then the k factorials cancel. So this becomes the limit as k tends to infinity of 2 times 1 over k plus 1. And now, as k goes to infinity, you have a denominator that's going to infinity, and other than that, you just have a 2. So that's going to equal 0. So by the ratio test, so it converges by the ratio test, because the answer we got was a number less than 1. So that's by ratio test. So I'm sure Lucas did something like that. Hopefully some of you were able to at least think along those lines. Again, if not, you're really going to have to just go and do some more chapter 8 work, because chapter 9 depends on chapter 8 every single step of the way. All right, so this is what would have happened if we plugged in a 2. Then that would lead to a chapter 8 problem like we just discussed. But we don't know that a 2 is plugged in. We have an unknown variable x. So what that means is that we have to basically approach it the same way, but we have a variable instead of the constant 2. So having just done all that, hopefully the way we do this example will then look pretty familiar. So to do the problem that we're actually supposed to do as a chapter 9 problem, we would do the same thing, but we would leave the variable. So to determine where this converges, since x is unknown, we basically apply the ratio test, but leave the x variable in there and set the result of the ratio test to be less than or equal to 1 and solve for x. And then we know what values of x would cause the series to converge. So then using the ratio test, we know that we're going to take the limit as k goes from to infinity of x to the k plus 1 divided by k plus 1 factorial. That's the x plus k plus 1th term, divided by the kth term, which when reciprocated would be k factorial over x to the k. So this should look exactly like what we were doing if there was a 2 plugged in there and we had a specific series. But now we don't have a 2, we have an x. So like before, this will simplify, because this cancels out with x to the k plus 1, just leaving x. And k factorial cancels out with k plus 1 factorial, just leaving k plus 1. So this gives us the limit, as k goes to infinity of x divided by k plus 1. And we need to figure out when would this be less than 1. What x values would cause this to be less than 1? Well, the thing to point out about this is that x does not vary with k. X is some number, and when you plug it in, it would be it would be fixed once you plug in a value of x, like we just plugged in a 2, and once you plugged in the 2, then that just stayed there. Oh, you know, I left off some notation, which actually will now start to matter a little bit, so I apologize. Let me put that back in. You may or may not recall that in the ratio test, it was always the absolute values that were used. So in order, the ratio test only applies when the terms are positive. And so because if I plug in a negative number for x, then I get an alternating series, and then I can't use the ratio test, what you will see is that what they're going to do is they're going to put absolute values on this. So let me do that. So I would put the absolute value on all this, because then that guarantees that my results are all positive. And when my results are all positive, then I can apply the ratio test, and then I get absolute convergence, because if the positive terms converge, then as we found in 8.5, then you have absolute convergence, which implies regular convergence. So I would basically, and k plus 1 is always going to be positive, so that would be reduced to this. All right, so back to where we were at. Sorry for that little backtracking. So the absolute value of x will be some number that doesn't change as k goes 1, 2, 3, 4, 5 and heads off to infinity. So I can actually pull that out of the limit. So what I end up with is that I have the absolute value of x times the limit as k goes to infinity of 1 over k plus 1. And I'm trying to figure out when this might be less than 1. Depending on which values of x I have, would this be less than 1? Well, the thing is that this limit goes to 0. And so it doesn't matter what value of x I have there. As soon as I plug in a specific finite value of x, then this limit will go to 0, and it'll make this product go to 0. So the overall result of this is 0 for all values of x. Let me write that with words. So what this means is the power series summation k equals 0 to infinity of x to the k over k factorial converges for all x values. So the original problem asked us to determine what is the radius of convergence and what is the interval of convergence. So if we're again thinking of centered at 0, but now since this converges for all x values, that means the x number line, all of those values converge. So the radius of how far I can go in either direction is infinite. So a whole number line here. So we conclude that the radius of convergence is infinite, and the interval of convergence would be the interval of the whole real numbers, which is negative infinity to positive infinity. Again, they do this for you as an example on page 676. So trying to sort of explain the logic behind it and the idea of what it's doing, because they literally spend about 1 inch doing it in 3 steps without really much good discussion. But I think this is a great problem for us to have some discussion about. So questions about that? So let's take what time we need to here, because this is a good example of what chapter 9 looks like. It has the language now in it. It has the idea of a power series and the idea of determining where does the power series converge, for what values of x can I actually use it to get an answer. There will be some like this where you have an infinite degree polynomial, and no matter what you plug into it, you get convergence, meaning its domain is all real numbers, and you can use it like any function. Of course, it is a totally different issue to determine what answer you would get. And as we saw before, that might be something you just end up doing numerically if it's not a nice power series or something. But that in general, you can at least understand that we have an infinite degree polynomial, and no matter what you plug in for x, it'll give you some answer. It'll converge to some value. Okay, so let's look at this idea of this radius of convergence. There's a theorem that's going to help us put this stuff together. So after they do a couple of examples for you, we have page 678. We have theorem 9.3. That discusses about the convergence of power series. So if we have a power series, and again, the general form is you go from 0 to infinity and you have some coefficients and you have x minus a to the k. A is the center, c sub k are the coefficients. So a power series converges in one of three ways. So the first possible way is what we just saw in the example that we just did. One possible way that the series converges is that the series converges for all x. If that's the case, as we just did, we say that the radius of convergence, which we're going to use big R for that, is equal to infinity, and the interval of convergence is the all real numbers interval, negative infinity to infinity. So that's a possibility, and we just saw that with our example of x to the k over k factorial. The denominator of k factorial just becomes so big eventually that it causes the terms to shrink down to 0 very quickly and causes the series to settle on a value no matter what you plug in for x. Two, so if it does not converge for all values of x, then there's some point in which it no longer converges. So the other next way that it might converge is that there's a real number, real value r greater than 0, some positive number of r, such that the series converges only up to r away from the center A. How would I write that? The series converges for, and this looks kind of like our epsilon delta definitions, for the absolute value of x minus a being less than r. And diverges if it's bigger than r. And so then we say the radius of convergence, this is r. And so what does that look like? Again, as we discussed before, A is the center, and that you start to think about deviating from A and seeing whether you get numbers that converge. And this says that basically you can add R to the right, going up to A plus R, or go, we'll say minus R, going to the left R, giving over to A minus R. And therefore you have an interval of convergence for all the values in here that you get convergence. Now this doesn't say what happens on the ends. That's still will change from series to series. We're going to talk about that a little bit later. But that definitely, as long as you stay within the radius of convergence value from the center, that will converge, and that if you go beyond that, it diverges. And the big reason this is a theorem is that it's the same in both directions. That if you're thinking about the center of the power series, that there is this distance that it's safe to travel away from the center in either direction in which you maintain convergence. And that once you surpass that in either direction, then you get divergence. So this is this is the second possible way that a series might converge, by having this finite R value in the radius of convergence. And the only other possibility, the third way in which it could converge and diverge, is that the series only converges at x equals a. Meaning you plug in an a, you get that first constant because that zeroes out all of the little x minus a terms. You always get convergence at a, because again, if you plug in an a in the general form, then all of these things get zeroed out. So whenever you plug in an a, you have to have the series converge just to the first constant term. The polynomial, it's like the constant at the end of the polynomial. So if that's the case, that means that if you deviate from A at all, you immediately get divergence. So when that's the case, then we say R equals 0. So then the radius of convergence is 0, meaning there is no distance you can deviate away from A and get a convergent value. You only get divergence. And in that case, you don't really write an interval of convergence because there isn't an interval, there's just a point. It only converges at A. So this theorem basically says that for all power series, the place that it works will always start with A, and if it goes anything better than that, it spreads out from that in both directions by some radius of convergence. And it's possible that in some cases that radius of convergence becomes infinite, and then you can plug in any number you want. Questions about that? Okay, so last thing for us to look at in this section, and then we'll try to take a little bit of a break. And then in 9.3, we go back to Taylor series. So the last thing we want to look at this section is how we can manipulate power series, because the title of this section is Properties of Power Series. Okay, so let's get a fresh page. Okay, so what can we do with power series? Well, they are summations. So we have some of the properties of basic summations, and we can see those expressed in our next theorem. So on page 679, we have theorem 9.4. And it's about combining power series. So let's say we have a couple of power series. So let's say we have, let me use the same notation they're using, C's, D's, okay. We have a summation of C sub k, x to the k, and we have a summation of D sub k's, x to the k. So again, each of these is a polynomial, and for this purpose, they've just done it in the simplest form where a is 0, but of course we could have some other a value in there. So then let's say these converge to f of x and g of x. So of course these would need to have this, they would both have to be convergent for some radius convergence. So we're going to say they converge to these functions on an interval I. So then these will look kind of familiar, but again, we have to just keep our minds around the kinds of things we're talking about, but these properties will look sort of similar to the kinds of things we've seen before. So the first way you can combine power series is with a sum or a difference. And that means if you made a power series where you had basically added all of these up, you had C sub k plus D sub k all times x to the k. And again, this would be if you just added up like terms of these two polynomials, then you would add up the coefficients. Then this converges to f plus g. And of course, if you had the difference, if this was C sub k minus D sub k, that would converge to f minus g. So basically, if series converge to functions, then the sum of those series converges to the sum of those functions. And that's also true with the difference. Of course, they both have to converge, so it has to be restricted to some interval of I where they converge. But the sum of the series, or the difference of the series, would be the sum of the difference of the values they converge to as a function. Questions about that? Basically, this is the kind of thing we always think we can do. If you're adding up two infinite series, then you can add up all their terms and the resulting converging values should be added as well. Okay. All right, so let's say that we have, next one is multiplication by a power. So let's remember that that these series are polynomials, so they have increasing power of x, like x, x squared, x cubed, et cetera, et cetera. So then let's say you have, well, I'll use the language they have in the theorem. So suppose we have an integer m. M is an integer such that k plus m stays greater than or equal to 0. That's a 0. As long as you're in the power series. Now, again, if k started at 0, then that would mean m would have to be positive, but you could have a power series where k starts at 5 or something like that, and then m could even be a -4. So they're just leaving open all of these sort of little possibilities. But the basic idea is that when you add k and m together, of course, you have to have positive non-negative powers. You can't have anything below a 0 because then you don't have a power series anymore. So if you have that, then what's their notation? Then let's say you have x raised to this power m, and that could be a -2 or a -3, but only if you multiply it with a k power, it always comes out non-negative. Usually it's going to be something like x squared or x to the 5th. And so then let's say that you multiply this by the series that we had up above, c sub k times x to the k. So we would normally think that this would lead to the idea that you could just put this inside, and this would give you the series of c sub k x to the k plus m. You would add the powers because you have the common base for those exponents. So the basic idea behind this is that this power here is always greater than or equal to 0. So you end up with a power series where the powers don't go below 0. You don't have any negative powers there. So that's sort of the setup, that you have something of that format. So if that's the case, then the result is x to the m times the convergent value of x for the function that you had before. Again, this is the same notation that we set up in the beginning of the theorem. We know that the c sub k's converge to f. So if we take the c sub k's and multiply them by x to the m, then that converges to x to the m times the f of x thing that it converges to. Again, this is over the convergence interval, but basically you could multiply all the terms of a convergent power series by some power of x, and that wouldn't change convergence. You would still get convergence. It would change the value you converge to because you're multiplying it by, this new thing, but it would still allow it to converge, and you would just get x to the m times whatever you got before you multiplied. Now, of course, if x is equal to 0, then you're multiplying by 0, and the whole thing would get zeroed out. So maybe the notation has lost some students. Are there any questions about this idea of what you could do here? Let's try a little example to illustrate that. We have an hour left. Okay, I just don't have time for another example. I'm sorry. I'm just trying to keep track of time. All of these things could be discussed, of course, for hours, but we only have the time we have. So then I'm just going to point to the fact that in 3, they do a composition. And again, it's in the book, so you can look at it and look at the several examples they give to play with these manipulations. So how does this allow you to manipulate something? It says if you have some, say, h of x, so this would be just a typical function, which is equal b times x to the fixed power m. Again, we have the same power m that we're dealing with. And so let's say that you plugged that into the power that you had before. So imagine that you have this and you plug this in. So then let's see, I'll write below it here, the summation as k goes from 0 to infinity of c sub k. And so normally up here you had x. So let's say we plugged into this function h of x, and then that's raised to the k. So notice what we did is we took this function and plugged it into the C sub k series that converges to f. So that if you have some sort of a power function, so b times x to the m is a power function, and if you plug that in, then this thing will converge to what you got if you plugged that into the value you got before for the power function. So basically, we plugged a power function into a known convergent series that converges to f. Then you can plug that power function into the f function to see what you would get as a result, and you'll still get convergence. That won't change any convergence. You still get convergence, and it converges to the function you would get if you plugged in h. Anyway, so this basically is some manipulations. You can multiply a power series by x raised to some power. That's the multiplication by a power. You can plug powers in. That's a composition. So then you're plugging a power in. And of course, you can add or subtract, take a sum or difference of power series. So the combining power series says we can do three things. You can add or subtract power series. You can multiply a power series by a power, just x to a power. And you can take a composition of a power function into a power series where you just plug it in to the power series, and that you still get convergence when you do these three things. That's the manipulative things that we can do. So a little bit rushed, I apologize, but again, we only have the time we have. And please take advantage of the tutoring that we just talked about, free Math Lab tutoring online, as well as come in with questions tomorrow at office hours or next week. But let's look at the last theorem that also is about how we can manipulate power series before we take a short break. So on page 680, we have theorem 9.5, next one on the list. And this is again about how we can manipulate power series. But this is bringing more calculus into the play. This is about differentiating and integrating power series. So let's do this a different way. Let's look at an example. So basically, I'm going to say with language what these two things say instead of just writing out the notation. You can differentiate a power series and still get convergence. And you can integrate a power series and still get convergence. They say this with a bunch of notation, of course. So this time, let's try it the other way. Let's look at an example to see what it's allowing us to do. Let's look at example 4. So we took note of the fact that the function 1 over 1 minus x is the result of a geometric series as long as you're plugging in a number that's got an absolute value of less than 1. So this, in those cases, is equivalent to the series as k goes from 0 to infinity of just x to the k, or 1 plus x squared, etc. And this is when the absolute value of x is less than 1. So this is one of our first and most important power series because it's just a basic geometric series. It's also a simple polynomial. All the coefficients are 1. And it has a radius of convergence of 1 and an interval of convergence from -1 to +1, not including the ends. Okay, so what could I do with this? Well, imagine that I had this equivalency, and that I took both sides and I took the derivative with respect to x. Well, the right side is the easier one. The right side is easier because we just have a polynomial and you can differentiate term by term. The left side, we have a little function, so we would need to differentiate this little function. So what would happen? Let's do the right side first. So the derivative of 1 is 0. The derivative of x is 1. The derivative of x squared is 2 times x. The derivative of x cubed would be 3x squared, and we'd get 4x cubed, etc. So if these two things are equal when x is greater than, when x is less than 1, then after I differentiate them, they're still going to be equal. That's what Theorem 9.5 says. And on the left side, how would I differentiate this? Well, if you take the derivative of this, basically you would use the chain rule. You would look at the bottom as being, I would look at this as being 1 minus x to the -1 power, which I'm differentiating. Then the -1 would come out front. 1 minus x to the -2 power. But then the derivative of the inside would pop out by the chain rule, which is just -1. And then those little -1s would cancel. So what I get, when I take the derivative of this, I get 1 over 1 minus x squared. So what does this mean? Well, it means that if you have a known power series, like we know that this thing gives us this, and you differentiate both sides, then you get a new power series. So this is a way we can figure out new power series from old power series. In fact, I can take this and write it as a formula. So that means 1 over 1 minus x squared is equal to the summation as k goes from 0 to infinity. And notice that the number in front of the x, the coefficient in front of the x, is 1 more than the power. So I can write that as by saying I have k plus 1 times x to the k. So again, this means you can take power series that you already know and differentiate them to get new power series. And we're going to start to accumulate power series. Basically, by the end of 9.4, we're going to have a list of known power series that we want to be able to use in problems. And so that's where we're working toward. And they do another example where they also integrate. Questions about how you can differentiate or integrate power series to get new power series? So it's kind of hard to think about what this means, but it means if I have this infinite degree polynomial on the right here, that as long as x is less than 1 in size, that it will converge to this formula on the left. And that if I had something like that, I could plug in like 3/4 or something like that. I could just plug that into 1 over 1 minus x quantity squared and get the answer for that infinite power series.